Good morning, everyone. My name is Sen, and today I'm going to talk about metric optimized example weights. And this is a joint work between Mahdi, Harry, Maya, and I in Google Research. And let's start with a motivational example. Suppose we want to build a ranking model and to rank some kind of, like, for example, documents or search pages. And the metric we care about is precision at 3. And we want positive precision at 3 globally. But we don't want to sacrifice the user experience in one locale for the user experience in another locale. So specifically, we also don't want to have negative precision at 3 in any specific countries. So we collect some data. The training data is from January to October, and the testing data is from November to December. So they are well separated. And we train the model, ranking model, with pairwise hinge loss. So the first attempt, we trained just a ranking model on the global data, and we get the result. The result shows that we got good global precision at 3, but the metric is negative in Japan and Brazil. So this may suggest that the Japan and Brazil data are underrepresented in the training data, so we should upweight them. So we tried attempt 2. So we upweight Japan and Brazil training data, and now we get good metric in Japan and Brazil. But now we get negative result in UK and India. So we do this again. We upweight UK and India training data, and now US turns negative. And this is actually the struggle that lots of practitioners face. That is, there are two issues here. The first one is the training distribution actually does not match the test distribution. The training data comes between January and October, and testing distribution is in the holiday season. And more importantly, our training loss does not match the testing metric. The training loss here is the pairwise hinge loss, but the testing metric we care about is precision at 3. So lots of practitioners face this challenge, and then lots of proposals are trying to address these challenges. And here we propose metric optimized example weights, and we call that MEOW. And our proposal actually learns the optimal weighting on training examples to maximize the testing metric. And our proposal is actually suitable for any loss, regardless if it's square loss, logistic loss, or pairwise hinge loss. It's suitable for any metric. And it could be a black box metric, it could be a non-differentiable metric, and it's also applicable for any model class, regardless if it's a logistic regression model, linear regression model, tree-based model, or deep learning model. We also provide theoretical analysis in the paper, such as the generalization bound. So under the hood, actually the MEOW incorporates two models. The first model is the main model, which is just a typical empirical risk minimization problem with weighted loss. And here the W term is the weight, and the L term is the classical loss we use, such as square loss or pairwise hinge loss. And the MEOW also uses another model, which is the weighting model, W. W has one parameter alpha that is learned to maximize the validation metric. And you can see that here. And the M hat is actually observed metric. And XV and YV are actually the validation data, validation features and validation labels. And the theta hat is actually the main model parameter. So we learned the main model and the weighting model iteratively. So here's a sneak peek of our proposal MEOW. And for more details, you can refer to our paper or come to our poster. So this is actually a two-dimensional plot on the weighting space. So our weighting model depends on two features, the X feature and the Y feature. And the dots are actually the weighting parameters that we optimize in the MEOW procedure. So at the beginning of the step, we try those weighting parameters basically randomly and uniformly across the weighting space. But as we go on, you can see our weighting model converges to the bottom right corner. That basically means we should upweight those features, those examples with larger X feature and smaller Y feature, like this. And as the training goes on, you can see at the beginning, this is the test metric. At the beginning, our test metric is actually lower and very noisy. But as the training goes on, the MEOW training goes on, our testing metric converges to a higher value. And for more details, please come to our poster tonight between 6:30 and 9 p.m. at Pacific Ballroom number 122. Thank you.